Before we get started.
Okay, elimination and miscellaneous things, on this first page there was an example of an E2 elimination right here in this long synthesis. Lots of chemistry that's more advanced beyond what we'll be doing. Or in organic 2, I think this reaction up here maybe is a standard organic 2 reaction. But right here we have an E2, iodine leaving group. What are they doing? They're eliminating. Iodine's gone, but also a beta hydrogen next door, H next door. Put in a double bond. There's 2 next door, so one of them will be anti-coplanar to the leaving group. DBU is a neutral nitrogen base. That's a classical, very straightforward E2 elimination. 96% yield reflux. 12 hours, okay? Not 30 minutes, okay? Apparently took a little time there, even though iodine's a great leaving group. DBU is not a super strong base. It's strong enough to do E2. Okay, where did we leave off at? Which compounds would give a positive silver nitrate test? Anybody? Which ones would give positive silver nitrate test?
The third group.
All of them except which one?
Everyone that has
The answer is everyone except which one? Which one will not give a positive silver nitrate test? All of them except the first one, yes, correct. Okay, why will the first one not give a positive silver nitrate test? Because the leaving group is not on a tetrahedral carbon, so it ain't going to ionize off and give a carbocation. Okay? We're doing leaving group chemistry on tetrahedral carbon. Leaving groups just don't up and leave sp2 carbons. Okay? The first page of the substitution handout at the top, tetrahedral, right? Okay, we mentioned this before. The next 3 will. Can the next 3 all ionize? Can the bromine leave and give carbocation? Yes. If this left, it would give what type of carbocation?
secondary.
Can you make a secondary cation? Yeah. How about this one?
Tertiary.
Not only would it be tertiary, it would also be,
Resonance.
okay? And the one on the end, can it ionize to give a carbocation? What type of carbocation will it be, Wyatt, on the end?
A mix of primary and secondary, right?
Yes, exactly. It's not just going to be primary. It's got resonance. I could call it a secondary carbocation. You could call it primary. Who's right? Neither. It's a blend between the 2. That's resonance. Yes, all 3 of those. Okay, we get rid of that one. Of those 3, which would give the precipitate fastest? That basically means which one's going to form the carbocation fastest, and which one is the bromine going to leave fastest? Well, that was going to be the best carbocation. It would be tertiary, but it would also be resonance stabilized and tertiary and secondary characteristics. Okay. If the leaving group ain't going to leave, then you ain't going to form silver bromide. And silver bromide is the precipitate, which indicates a positive test, right? Okay? Number 2, I'm not even sure. Number 1 was apparently silver bromide, but what is 1 and 2 under? We're looking at how to promote ionization to the carbocation. And with halides, we can use silver ion as a, what type of acid? Lewis acid, yeah, okay. Polar solvent, look at these 2 examples. If you take this alkyl bromide with this alcohol and heat it in such a solvent, a polar solvent, a polar non-nucleophilic solvent, such as acetonitrile or DMSO, you can look these structures up. These are 2 very common polar non-nucleophilic solvents. They're also aprotic. Get a reaction. Is that substitution or elimination? Clearly substitution. The O has replaced the bromine. What's the mechanism? SN1 or SN2? Clearly SN1. There's no strong nucleophile. SN1. What's the break determining step? Forming carbocation. Okay. Yes. If you try this reaction down here and using a nonpolar solvent such as hexane, well, I wish you good luck. It probably ain't going to work. Why not?
Not to take the water.
That's a Bill Gates is rich. He's got a lot of money. Why? Why does nonpolar solvent make that reaction not work? Well, what's the rate determining step here?
The carbocation forming.
Making a, is this polar?
No.
It's an ion.
Oh.
That's the definition of polar. Right? What does polar mean? Okay, it's an ion. Ions are polar. Okay, hopefully you heard that in Gen Chem. Okay? What type of solvent is going to facilitate or make this happen? Polar solvents facilitate polarization. What happens when you put HCl into water? It does what? It ionizes because it's in a polar medium. Okay? And you get these ions. Okay? I mean, we can show it like this, and Cl minus. And then the polar water starts loving these, hugging them, hugging it. IMFs, right? Okay? Polar solvent will start giving this some love and good IMFs. Okay? What if you make this in the presence of hexane? Is hexane going to be loving this ion? No, it's going to shun it. It's like, I don't, get away. Okay? There's a transition state from here to here. In the transition state, the solvent can be involved and start hugging it and stuff and helping it along the way. Polar solvents facilitate forming polar ions. Okay? Non-polar solvents are just the opposite. They don't facilitate it. It's going to be a tough reaction if you try to use hexane as solvent. Okay? We don't talk about solvent too much. I don't. Does this make sense? If you want to make something polar, you want to use it. You want to let it. You want to give it a polar environment to form it. Like likes like. Like dissolves like loves like. Okay? So, use a polar solvent if you want to facilitate ionization. Okay, different topic. Deuterium isotope effect. This is a neat way to determine if an elimination reaction is E1 or E2. Look at this reaction here. First off, is that an elimination reaction?
Yes.
Yes. Second, is it E1 or E2? Who says E1?
It's got to be E2 because it's no rearrangement.
Who says E2? Okay, I see 4 people voting. Okay. Gabor, why do you say E1?
sp3, sp3 nitrogen or
This nitrogen is not sp3.
It's sp2.
This nitrogen, which is started as a base, this lone pair is in what type of orbital?
P.
sp2, not a P. sp2.
strong.
Everybody agree that's acting as the base here?
Yes.
Took the H. What H did it take? Took this beta hydrogen here. Okay. We removed HBr. Okay. What's the mechanism though? Why do you say SN1? I mean E1.
It's not strong enough.
What does E2 require?
A strong base.
Strong base. The question is pyridine, that's called pyridine. It's benzene with a nitrogen instead of a carbon. Is pyridine strong enough to do E2?
No, it's not an anion or an sp3 carbon or an nitrogen.
I agree with that, but that's a very sort of strong statement. Are there any exceptions to your statements?
Most probably yes.
Most probably. So, I used to say, like a couple months ago, maybe SP2. Stop saying that. Question is really, is pyridine strong enough for it to be bimolecular, or is it going to be unimolecular? Do we just say, it's hard to know? Or could we come up with a neat way to determine the answer? How about a neat way to determine the answer?
Yeah, that's good.
Deuterium isotope effect. Yes. Can we tell the answer from anything else? Stereochemistry. Am I showing a Zaitsev or Hoffman product?
Say so.
Showing a Zaitsev product. What if I showed a Hoffman product? What would the mechanism be?
E2. E2 for sure.
Why would that mean it's E2?
Because E1 reactions can't yield Hoffman products, they yield the Zaitsev product.
Very good, yes. I don't know that we ever stated that, but we stated it another way. E1 gives what product?
The most stable.
Most stable. Hoffman ain't the most stable. Okay? What's the idea? I'm showing a Zaitsev, and Zaitsev can be E1 or E2. Okay? As shown, I don't know. Okay, neat way. What we can do is a deuterium isotope effect. By the way, before we look at that, tell me how you would use rate information to determine. How would you use rate information? By the way, why does it matter what the mechanism is? Oh, it matters. Maybe I'll comment later. Let's get straight to the point here. How would you use rate? Devise an experiment for rate.
You not just see which one has the rate determining step in the carbocation formation.
How would you do that?
Add some more pyridine. Add some more pyridine.
Add more pyridine and look for what?
Changes in the rate.
Changing the rate. Do the reaction, okay, baseline. Do the reaction again with change the concentration of pyridine and see if what?
The rate changes.
If the rate changes. What if you add more pyridine and the rate increases?
Then it's
And that's
E2. It would be
It means it's E2.
bimolecular.
What if you add more pyridine and the rate stays the exact same? There you go. There's one way to tell if it's E1 or E2. Rate experiments. That's what I said in number 1 down here. Is that right?
Yes, sir.
Yes. Okay, what's the second way? The second way is deuterium isotope effect. Replace the beta hydrogen with a deuterium. What is that? What is that? Deuterium.
A 2 neutron.
It's just a hydrogen with an extra what?
Neutron.
Well, it's not an extra one. It's a hydrogen with a what?
Additional neutron.
Neutron. My very first handout I gave you described deuterium. Okay? It also mentioned that it's often used in organic for various reasons. We saw it on the quiz, right? Okay? It's just a fancy H. Okay? But because it's different, it allows for things like stereochemistry. But you have an H and then a fancy H, they're different. But the carbon is still maybe primary. Because if there's a D there, you don't consider the carbon now secondary. Okay. Replace that H with a D. That can be difficult to do. D stands for difficult here. But theoretically, it can be done. Okay? Then do the reaction and see if the rate is slower or not. Question. In which mechanism is the H removed in the rate determining step? In this case, D. In which mechanism is the beta hydrogen removed in the rate determining step? E1 or E2?
E2.
E2. Yes. Okay? But not in E1. All right? Because you know the mechanisms. Now, a CD bond is stronger than a CH bond. Deuterium, the mass of deuterium is 100% greater than the mass of H. Mass of H is 1. Deuterium has a mass of 2. It's 100% greater. It's a huge difference. And strengths of bonds do relate to mass of atoms. That's never really talked about. It's just a mass effect. That bond is about, I think, 7 times stronger. Okay? Not sure. Think about it. Okay? It is stronger. A stronger bond is going to be harder to break in that rate determining step. But that only matters, that's only going to affect if the mechanism is what? In which mechanism is the CH or the CD bond broken in the rate determining step? E2. So it would only matter for E2. Is this bond going to be broken in the E1 rate determining step? No. So it wouldn't matter if the bond is stronger. Okay? So we can do that. And replacing the H with the D, that would be called a deuterium isotope. Because deuterium is an isotope of hydrogen. What effect would that lead to in the rate? That's commonly done. So again, that reaction is shown. It's sort of, it's hard to predict if it's E1 or E2. If you say the pyridine is weak, then you're saying that the mechanism must be E1. I think that's probably E2. I think pyridine might be strong enough, but I'm saying might. If you want more proof, there are a couple of ways to get more proof. Why does it matter? Maybe you're doing this reaction for, you're working with a company, you want to make this compound or some drug that has a similar reaction, and you want to improve the rate. You start, well, let's just add more pyridine. That should make it faster. No. Not if it's E1. If it's E1, you're wasting your money adding more pyridine. And if you're wasting the company's money, they're not going to like it. They're going to say, did you not first check and determine that if it was E1 or E2? Why are you just wasting all this pyridine? Which, by the way, is also kind of toxic. Okay? So if you want to modify your reaction, it's good to know what the mechanism is. Okay. Is there a question? Yeah.
So if you wanted to determine the E1 or E2 for the reaction, would you need experimental data to support it? Or is there any way to do it by hand?
No. We looked at it. Strength of base, chemical outcome. There's nothing there that I can see to help you determine without some actual data. Rate data. Deuterium isotope effect. Because we make these statements to help us determine mechanisms, but sometimes you can have some ambiguities. I don't know. We can just say, well, we don't know. Or we can talk about ways to solve that I don't know. Okay, homework, how'd we do? Substitution product for the first reaction. Anybody got something? Anybody got something that you want me to look at? Anybody got something? Anybody got something for the second one? All right, let's look down at double E2, lab this week. Not a James Bond movie, way to make out time. 2 leading groups. You take this compound here, treat it with 2 equivalents of this. What is this? Potassium tetroxide. What type of reaction is that? What's
Strong.
strong? What else can you tell me about it?
Sturgeon hindered.
It's a strong steric hindered base. We mentioned it more than once before. What type of mechanism does this look like? We got leaving groups on tertiaries or carbons, so we can do substitution or elimination. What do you propose? Strong sterically hindered base sounds like what?
Elimination.
E1 or E2?
E2.
E2, yes. Okay. Which leaving groups we're going to eliminate first by E2? Hard to say. Hard to say. I don't think we've talked about it. We can eliminate either one. Down here, the leaving groups are on the same carbon, so they're eventually identical. Up here, they're not. We could eliminate here, okay, and that would give that double bond, is that right? Would these groups be cis or trans? Maybe cis or trans. Well, we can think about that. From here, though, that's just one elimination. From here, though, we can eliminate again, okay, minus HCl. We can eliminate again minus HCl, and what does that give? We now remove HCl, and we put another pi bond in. When you put another pi bond in, what do you have? Alkyne, okay? And so it's a double E2 elimination. A double elimination of HCl. Down here, double elimination. The product would be, see down here, the only place you can eliminate is between here. There's no beta hydrogens here. Double eliminate here. We got triple bond between those two carbons. This carbon has an ethyl, and this carbon has a what? Phenyl. Note that your sp carbons are linear, right? We learned hybridization geometry back for test 1. I sometimes see you guys draw products like this. It's quite ugly, right? An alkyne is linear, right? Double E2 elimination. Any questions about these? I can imagine a variety of questions, but I'll let you ask so I don't waste time here. Questions?
So how exactly would you go about showing the mechanism for the elimination of either one?
It's E2, right?
Right. So we can just show E2 both chlorides?
Yeah, it's a double E2 elimination. Yeah. Do an E2 and then do it again.
Okay.
Yeah. There's an intermediate down here, right? What's the intermediate? What type of functional group does the intermediate have? That is, after you do one E2, you get a what? Alkene. And then when you eliminate again, you get the alkyne. Yeah. I didn't show the intermediate down there.
Once you form the alkene, is there a way to stop it?
Good question. Maybe one equivalent of base. I think it would probably stop. Because there's another huge question that could be asked here. I was hoping that somebody would. Related to that.
Energy of activation?
What?
Energy of activation?
Yeah, but more specifically what? Nobody have a big problem with Anything up there? Okay, basically double E2 elimination. All right, let's see where we're at here. On the back, deuterium. Deuterium is being seen more in drugs, taking advantage of the isotope effect. This compound here is a drug used to treat HIV. What type of ring is this out here on the end?
Pyridine?
Yeah, this pyridine ring in the body is oxidized, and an OH group is put here by metabolism, oxidative metabolism by the body. But when this happens to the drug is no longer active. Okay? And so if you want the drug to last longer, which sometimes you may, you want to stop the metabolism or slow it down, right? Metabolism kills the drug. One way that they have chemists, medicinal chemists, whatever pharmacologists have come up with, is replace this H with a D. Does everybody agree that when this drug is metabolized, the CH bond is broken? It's no longer there. It's now a CO bond. If we replace it with a D, that bond will be stronger. And the metabolism could be more difficult, assuming the bond is broken in the rate determinant step. Because if it ain't, this ain't going to work. But this is known to work. And so the drug, you can replace the H with a D, and that is known to slow the metabolism of the drug down. Okay? Make it last longer. And then maybe instead of having to take 3 pills a day, maybe the patient only has to take 1 pill a day. And so you're going to get much better compliance, etc. As long as replacing the H with the D doesn't change the drug activity. But H to D is a very small change. It's just having 1 extra neutron in that site. Very minor change. Yes.
Can we go back to that page?
Which page?
The one there you're asking questions.
Back over here. Question?
So, is the reason that we can't, so how would we be able to go about doing, like, taking out the other CL because it's an sp2 carbon?
Very good question. Yeah. When you do the second elimination, the leaving group is on what type of carbon? It's on sp2. Nobody was concerned about that because we said tetrahedral many times. Yes. Whenever we do the next elimination, again, I'm not sure which structure it is because I'm not taking the time to think about that. But let's consider here. There's the H there. It's gone over there. The base, right, the tert-butoxide, got a second equivalent. Okay? Take the H. Can you do an E2 elimination here?
Yes.
Well, I mean, assuming you can, but can you actually show it? We eliminate the H in the leaving group, all concerted. But the leaving group's on an sp2 carbon, not tetrahedral. Great question.
That's it.
That's whose?
That's
Your question? Is your proxy here? Now I'm telling you, you can get alkynes. You're also making one in lab. Did anybody make an alkyne yesterday in lab? Are you sure you did? What proof do you have? Because maybe I'm just I'm messing with you. You have proof that it was an alkyne product?
We took an IR yet, but we didn't.
Probably the melting point. Melting points are different.
And you're comparing your melting point to what?
No, I haven't taken the lab, but I'm thinking the melting point should be different.
Okay, you're comparing it to a literature melting point for an alkyne?
Yes, sir.
Okay. Okay. And so, if the alkyne is actually formed by the double E2, then the second E2 must occur, the leaving group is leaving not from a tetrahedral carbon, but from an sp2 planar carbon. And I've said that you can't do that. I've said it more than once. I said it earlier today. Well, here's an example where you can. Okay? And I kind of cringe at showing you this. But we're doing it in the lab. It can be done, but it is more difficult. And it does require a good amount of heat. And I cringe at this because I don't want you to get in trouble. Don't start doing this with other places. Okay? There's a very rare exception of a leaving group leaving from a non-tetrahedral carbon. Okay? Everybody agree that that is a huge exception to what we've sort of stated several times? Okay. But thanks for recognizing it. Yes. The second halogen is leaving from a sp2 trivial planar carbon. Yes.
Oh.
Yes. Okay, how about substitution handout? Now we're already on the very back here. I usually showed this earlier, but we did not. This is the synthesis of Zyrtec, an antihistamine. Have I ever taken Zyrtec? No?
Yeah.
Okay, there it is down there. Here's the synthesis of it. Now this is actually lots of basic chemistry that you've either seen or you will see in organic too. Okay. The other one I showed you today had a lot of sort of advanced chemistry. A lot of standard chemistry here you will see. And anytime I write stuff in, it's sort of alluding to that. You'll see Grignard reactions in organic too. Okay? Things. Look right here, going from 42 to 43. What are they doing? Compound 42 has leaving groups. Really only one. Which one is going to be susceptible to
Bromine.
bromine? Yeah, because the chlorine is not on a tetrahedral carbon. And the only exception that I know that you should be aware of where it can leave from a non-tetrahedral carbon is in that double E2. I know of no substitution reaction is going to work if the leaving group is not on a tetrahedral carbon. Okay. That's another exception to that crazy thing we just saw there. Question?
So even if there was like lots of heat, you wouldn't allow the leaving group to leave off the S2 in this case?
Not by an SN2. You can get a different substitution, and you'll learn that in organic 2, but it will not be SN2. You do not do SN2 unless you don't tetrahedral carbon. No exception that I know of. Okay? Or SN1, or E1. The only exception is in E2, when you do that double E2. I know of no other exception. Okay? You're not going to displace this chlorine by any mechanism we've seen in this class. Because you're also not going to do an E2 there. Well, E2 possible, we won't go there. What's going on here? We don't have to, we see what's going on. Look, that carbon, nitrogen is now bonded to it. How did it get there?
Substitution.
A substitution. Right here is that this acted as a nucleophile and came in here and kicked that off. Can you do, I'm doing SN2. Can you do SN2 on that carbon? It's secondary. Can you do SN2? Yeah. What if it was tertiary?
No.
No, that's bad. Okay. By the way, which nitrogen is nucleophilic? The left one or the right one? Why not the right one? Right one's conjugated. Okay. Here you go. There's your nucleophile. They're including carbonate. This is done in xylene. We've seen reflux 10 hours. Why carbonate? By the way, in this reaction, this group over here has been cleaved by the second step. That's why it's no longer there. But after the first step, it is there. You see how an H has been removed from this nitrogen? What removed it? The carbonate base removed it, okay? As you go back to when we showed direct alkylation of nitrogens, I showed inclusion of a base. Is that right? Remember this scheme here? What was this? An alkyl bromide. Ammonia displaced the bromine from the carbon. It's going to exist like this until you include what? A base. Only when you include a base are you going to go back to the neutral amine. I talked about that. Okay, that's the purpose of the base. We went back to the neutral amine. All right. The second step, leave that off. Don't worry about that. I'm saying the first step is SN2, but I said most likely. After we confirm if it's SN2 or SN1. We already talked about the rate. Right? Why does it matter? Well, we already talked about that. Basically, that's an example within the synthesis of just using an amine as a nucleophile. Picking off this leaving group. Not that one. No way. And then from there, continuing on. Actually, the very next reaction is also an SN2. What then happens here? This one then comes in here and kicks off that chlorine. Yeah? Right? Chlorine's gone, nitrogen now bound. Where'd the H go? What took the H? Cl minus ain't going to take the H. Look back at that thing I just showed you. What's in here to take the H? Triethylamine is acting as a base to take the H.
Isn't this actually?
Okay? What can we look at, guys, to finish up? One thing I'll show you is, yesterday I sent out by email something that the student sent to me. It's some reviews, look pretty good. Okay. Here's another review that's out there. You can find a variety of things. Determining how reactions go. Predicting SN1, E1, E2. It's from the Journal of Chemical Education. Let's see if this sort of makes sense. Determining major reaction type. Questions? Is there an sp3 carbon with a leaving group, typically halide or tosylate? The answer is yes. All your mechanisms are theoretically possible until we rule out otherwise. The answer is no. None of them are possible.
Exception.
Well, hold on. We just showed that E2 is possible, right? Okay. We need to let them know that E2 is actually an exception. Not only did we see in lecture, you're actually doing it in lab too. Okay. But you understand, it's really an exception. And these people actually say, no way. Okay. So what if you do have a leaving group on a tetrahedral carbon? What could be the next question? Is there a beta hydrogen? Because if there is, you're still able to do all mechanisms. But if there's no beta hydrogen, what mechanism can you not do? If there's no beta hydrogen, you can't do elimination. Everybody agree? Pretty straightforward. Is the beta hydrogen coplanar with the leaving group? Or I would rather say, can it become coplanar? Well, maybe it's not as drawn, but maybe it can rotate. Can it become? Because if it can't, guess what? You're not going to be able to do E2. If it is, then you can still do all of them. Is there a very strong base present? This diagram differentiates between very strong and strong. I've never done that. I've just said strong or weak. And I don't, okay. Yes, if your base is like super, super strong, it'll prefer elimination. We kind of said that. Didn't we say bases prefer elimination? Nucleophiles prefer substitution? I didn't really use very strong terminology. Neither. What if your base is not strong? What does that rule out? It rules out E2. See how E2 is gone? Okay. Structure of substrate. Leave a group on tertiary. If the answer is yes, what is it ruled out? It ruled out SN2. Okay? Leave a group on primary. What does that rule out?
Everything except SO2.
That's going to rule out SN1 and E1, because you don't make primary carbocations. And maybe, okay, solvent. We talked a little bit about that. Solvent stuff is, I wouldn't consider too much beyond what I've talked about. Some instructors, some textbooks talk about solvents a little bit more than I have. What if you got SN1 or E1 that are both possible? How could you distinguish? Well, maybe heat. Which one does heat favor?
Elimination.
Heat, yes. Doesn't heat favor elimination? Did we say that? Okay. You can look at other things. So these types of charts are out there. Okay. I went through it quickly. Did most of the points I made we've already heard before? Okay. It's all there. Okay. I can send you this by email if you like.
Yes,
Yeah, we
please.
like that.
Okay. You got to be careful though, guys. You can't, and I didn't start with this. No way would I ever start with that because you guys just want to kind of memorize. But you can go back and look at it now and sort of confirm your knowledge. Okay. There may be some things there that we didn't talk about. Again, I'm not talking about every single thing. I'll send that to you, but be careful about it. I'll also send you a UV Viz handout for Monday. Any last questions, guys? Okay, we'll have a quiz on substitution elimination on Monday. We'll probably be doing UV Viz. I'll also see if there's any last questions about test-3 material. See some of you in lab. If you want to start at 2 o'clock, that would be good.